All right, let's get started. Welcome, everybody. My name's Brooke Heffright. I am the director of CINA at George Mason University. Uh, Today, I am pleased to present the results briefing for the project entitled Exploring Graph Neural Networks for Attributed Multilayer Criminal Network Analysis. Our presenters will be the PIs on the project, Assistant Professor Suhang Wang, uh, who, and I don't believe he's on the line today, but his co-PI was Professor Vasant Honavar. Both are at the College of Information Sciences and Technology at Pennsylvania State University. So CINA is a DHS Center of Excellence hosted by George Mason University. CINA, C-I-N-A, stands for Criminal Investigations and Network Analysis. And our mandate is to further the mission of DHS in countering transnational criminal organizations. DHS Centers of Excellence are managed by the DHS Science and Technology Directorate's Office of University Programs. The goal is to conduct groundbreaking research resulting in rigorous, objective knowledge products and timely solutions for DHS components. I see our program manager, Corey Davenport, is on the line. Dr. Davenport, would you like to say a few words on behalf of OUP?
Sure. Thank you, Brooke. So good morning. I'm Corey Davenport, the DHS Office of University Programs Program Manager for CINA. As Brooke mentioned, and while most of you are probably already aware, among other activities, the Office of University Programs currently oversees 9 active centers of excellence, of which CINA is one. I know Dr. Wang and others have put a lot of time and energy into this very cutting-edge project to improve criminal network analysis. I'm very much looking forward to hearing the results. So thank you.
Thanks, Corey. All right, just to make it a little bit more concrete, the way that the COEs work is that George Mason receives funding annually from OUP to fund research by scholars at institutions all over the country, and in several cases in allied countries. And so that is the pathway to the research that you'll hear about today, which is just wrapping up. Now, the methods in CINA's research portfolio include criminal network analysis, dynamic patterns of criminal activity, forensics, both cyber and traditional, and criminal investigative processes. And today's research addresses both criminal network analysis and network analytics. In addition to funding, fostering, transitioning research, CINA's mandate includes conducting education and workforce activities to prepare the future DHS workforce and to develop the current workforce. Our activities include the 3 summer research teams from minority serving institutions that Mason faculty hosted this summer, as well as interns that CINA supported at DHS's Cybercrime Center. And we're very eager to continue both of those activities in the coming year. CINA also has a mandate to host events and conduct outreach. A good example is our ongoing Distinguished Speaker Series. Our next speaker will be Donna Turner, a former Bank of America executive, now with the nonprofit The Noble, on October 9th at noon. If you don't have an invitation or you haven't registered yet, please feel free to reach out. You could just reach out through the chat, and our events coordinator, Sarah Subsiri, will add you to our mailing list, or you can navigate to our website. That's at cina.gmu.edu, CINA with a C, cina.gmu.edu. And this particular installation of the speaker series will be a joint event with The Noble, a nonprofit based in Chattanooga, Tennessee, that focuses on combating cyber-enabled human crime by bringing together the nonprofit sector, the financial services industry, and government. Now, CINA is supported by a DHS board of directors. I see several of them on the call today. They help to ensure the relevance of our research and to identify champions and funding for transition. But CINA is a resource for the entire Homeland Security enterprise. In addition to a cooperative agreement, which defines us as a center of excellence, CINA also has a basic ordering agreement recently renewed for 5 years, which we can use to facilitate transfer, licensing, and commercialization, as well as to conduct bespoke research on behalf of interested components. If you are interested in the research you hear about today, or in conducting research with CINA or any of our activities, please reach out to folks today or through our website, and we can help set you up. So without further ado, I will turn it over to today's speaker, Dr. Suhang Wang of Penn State University.
Thanks very much for introduction. Can you hear me?
We can hear you just fine.
Okay, great. Yeah, so I'm very glad to present our project titled Exploring Graph Neural Networks for Attributed Multi-Layer Criminal Network Analysis. So my name is Suhang Wang. I'm an associate professor of College of Information Sciences and Technology at Penn State University, and Dr. Vasant Honover is the co-PI of this project. So here's the agenda of the project. I will first give some background information and overview of the project, then talk about some technical details of the project, followed by the application and the stakeholder engagement, and finally talk about transfer of tech and the results of the project. Okay, so first, as we all know, criminal network analysis is very important when applied to the investigation of organized crime like fraud, armed robbery, and terrorism. Therefore, many criminal network analysis tools or methods are developed. However, most of the existing methods, they simply treat a criminal network as a single-layer non-attribute graph. By single-layer non-attribute graph, I mean some graph shown in the figure, which is only composed of node and edges connecting the nodes. Here, the node may be the criminal, and the edges may be some interaction or relationship between criminals. Then, existing method would adopt some social network analysis tools to analyze criminal network. For example, for linker predictions, they might adopt some classical method like J-card coefficients, common neighbors. To detect community, they might adopt something like modularity maximization. And to interrupt the network, they will adopt network centrality to find influential nodes in the network, then remove those nodes. However, real-world criminal networks or maybe social networks, they are much more complex, which contains richer information and require more advanced graph mining technique to analyze them. First, like real-world criminal networks, they might be multi-layer, with each layer contains a network representing one kind of relationship. In the figure, I show a three-layer multi-layer criminal network. The first layer is the meeting relationship. The second layer is a phone call relationship. And the third layer is a coactivity relationship. And across these layers, they share the same set of nodes, where each node here can be one criminal. So those different layers, they contain correlated but complementary information, which would be very helpful for criminal network analysis, such as linker prediction. For example, if I'm interested in coactivity prediction, right? I want to predict some missing links in the coactivity layer. Maybe the coactivity layer is very sparse, so it would be very helpful if I can leverage the other layers, such as meeting and phone call layer, which has very high correlation with the coactivity layer. So leverage those layers would be helpful to do link prediction in the coactivity layer. Secondly, real-world criminal network might be attributed. So we might be able to obtain attributes of criminal, such as his or her personality, skill set, and the possession of particular resources. So those information would be very helpful for some tasks like identifying the role of the nodes in the network and performing network disruption. So therefore, it is very important to develop some kind of technique to handle such kind of complex multi-layer attributed graph. However, existing simple social network mining tools cannot handle that. So recently, graph neural network have shown great ability in modeling complex graphs in various domains, such as biology and knowledge graph. Generally, you can kind of think a graph neural network is an extension of neural network on graph structure data. So it's able to learn vector representations of node that captures the graph structure information and the node attributes information. So that the learned vector representation of each node would be very helpful for various kind of tasks. Therefore, it would be promising to explore graph neural network for attributed multi-layer neural network analysis. So the goal of the project is to systematically study new frontiers of attributed multi-layer neural network analysis with graph neural networks. In particular, we focus on 3 tasks. The first task is develop a graph neural network for attributed multi-layer neural network modeling. We want to develop a novel graph neural network so that it's able to handle the complex graph structure to learn node representations that would preserve such kind of structure and node attributes. And secondly, based on the model we developed on the first task, we want to further to utilize it for effective multi-layer neural network disruption. We want to remove few influential nodes or edges within the budget so that we can maximally disrupt the functionality of the network. And we also observe that the newly emerged criminal network or newly collected data, they are usually very noisy, incomplete, and lacks label information. Meanwhile, we have some more mature multi-layer criminal network data that would be more dense, contain complete information or label information. So we want to develop some transfer learning technique to transfer the knowledge from those material graph to sparse noisy graph to alleviate the issue of noisy, incompleteness, and the lacking of label, so that we can facilitate some tasks like node classification and link prediction. And along the projects, we also developed a toolbox for attributed multi-layer network analysis, which includes the state-of-the-art and the representative algorithms, publicly available data sets, and some modules for network visualization and measurements, and some evaluation modules. So next, I'm going to introduce some technical details for each task. For the first task, we want to develop a novel graph neural network for representation learning on attributed multi-layer neural network so that the learned representation can facilitate various downstream tasks. The main challenge is that since we have a very complex multi-layer graph structure, right? So how can we simultaneously capture node attributes, interlayer, and intra-layer structures in multi-layer network? And meanwhile, how do we make sure that the learned representation would be very helpful for the downstream task? So our approach is to develop something called a multi-layer graph neural network. The multi-layer here doesn't mean that simply stack multiple graph neural network layers, but some kind of special design to handle the multi-layer graph. And meanwhile, we design some loss function to be integrated into the learning process of multi-layer graph neural network to facilitate downstream task. So here's an illustration of one layer of the multi-layer graph neural network. Essentially, you can kind of think that we try to learn some representation of node so that this representation can capture the graph structure information and node attributes information. So the way we learn the node representation in each layer is by first doing some aggregation on each layer, right? So that it can capture the information of local graph structure information in each layer. Then we'll do some so-called attention-based interlayer aggregation to aggregate these different layers. During the aggregation, we'll assign different weights to each layer so that that's because some layers might be more important for the downstream task. Some layers might be noisy or less important. So we design some mechanism to assign different weights to those important nodes and the smaller weights to non-important nodes finally, we combine those layers together to get node representation. Okay, so that's one layer of the MGNN. We have multiple layers to better capture the longer hop of the graph. So now next, I'm going to demonstrate how we use such kind of structure for some tasks like node classification. Okay, the problem of node classification is like this. We are given an attributed multi-layer graph with a small portion of the nodes labeled. And we want to learn a node classifier on this graph to predict the label of the remaining nodes. The main challenge here is the different node might need different layers information for node classification. And meanwhile, the label we get is only a very small portion. So how can we train a model, a graph neural network model, to effectively doing node classification? Here's an illustration of the model we developed. First, we have the graph multi-layer attributed graph as input to our model. It's used as input to this attention-based multi-layer graph neural network, whose structure is just shown in the last slide. Okay, so after this, the attention-based multi-layer graph neural network, we have got the node representation of each node, right? That's kind of vector representation. You can kind of think that's some extract feature from the graph that captures graph structure information and the node attribute information. Then this node representation is used as input to the classifier to map it into label. However, directly training the model is suboptimal because the amount of label we have is very small. So we also utilize the contracted learning, which is kind of self-supervised learning technique to help learn better representations to facilitate the node classification. We also developed a mechanism to regularize the attention score. Just a record attention score is during the aggregation, we will assign different weights to different layers because the different layers might have different effect or importance for the downstream task. And we develop some mechanism to do some regularization to better learn those attention score for the downstream task. So that's what the model look like in a high level. And once the model is trained, then we can utilize the trained classifier here to predict the label of the unlabeled nodes. I'm going to quickly introduce some experimental results. We did experiments on some publicly available data sets like ACM, IMDb, they are 2-layer graph, DBLP, Amazon, they are 3-layer graph. We use 30% of the nodes for training, 10% for validation, and 60% for testing. The last 2 layers are the experiment as a result of our framework. So we highlighted the best results in the bold font. As you can see, our framework achieved the best result. Since we do not have, we didn't find any publicly available attributed multi-layer graph, we also generated constructed a synthetic 2-layer neural network graph with 400 nodes and 2 layers. The first layer is money transaction. The second layer is information exchange. So we designed 3 kinds of node labels, and we sampled the edges between different layers and different type of nodes using different kind of distribution to simulate the neural network. For the node attributes, we use the GPT 3.5 Turbo to write a description based on the label of each node. We then convert the description using bag of words to get the node attributes. So we did test our model on this synthetic data set, and the last row is the performance of our model. As you can see, our model significantly outperforms those baselines. We also tested the multi-layer graph neural network for link prediction. Just a quick review of this task. Given an L layer attribute graph, where the else layer is very sparse, right? Maybe the else layer is a coactivity relationship in the example I just mentioned. So we want to leverage the 1 to L minus 1 layers to help predict the missing layer link in the else layer. So the main challenge is, well, not every layer are useful for the link prediction for the else layer, right? Some layers might have positive correlation with else layer. Some layer might have negative correlation with else layer. So how can we select or assign different weights to these layers for the link prediction in the else layer? And secondly, the target layer is very sparse. Similarly, we use the graph. We use the multi-layer graph neural network to learn node representations, and then we integrate the learned node representation into the target layer to help facilitate link prediction of the target layer. Okay, so I'm going to skip the details of this. If you are interested in it, you can refer to our paper. Essentially, we'll just you learn node representation from the 1 to L minus 1 layer and use those node representation to construct a graph to make the target layer more dense, and then utilize this constructed graph to predict the missing links in the target layer. So here's the experimental results. Our model is called SMGNN. We compared with the state-of-the-art method, including graph neural network and multi-layer graph neural network. So as you can see, again, our framework outperforms all the baselines. We also tested it on the synthetic data set we constructed. As you can see, for the 2 columns of SMGNN, the model proposed by us also significantly outperforms the baselines. So the second task is the graph neural network for effective multi-layer neural network disruption. The goal is try to remove few influential nodes or edges within budget to maximally disrupt the functionality of the network, such as maybe lowering its information flow, or making the originally connected graph disconnected, or maybe maximize the average short path length. So this is a very challenging task because the removal of nodes is discrete operation, which makes the training of our model using gradient descent very difficult. And secondly, the criminal network is resilient. It might recover by replacing the role of removed nodes with other nodes, or maybe it will introduce new node to replace those removed nodes. So to handle those challenges, we formulate it as a reinforcement learning framework with the multi-layer graph neural network. The reasons that we choose reinforcement learning is because it's very good at handling discrete operation, and meanwhile it's able to interact with the environment. So it allows us to take the recovery of a neural network into consideration. Here's an illustration of the framework, where we have GT is the intermediate graph at the T step, and this multi-layer graph is used as input to multi-layer graph neural network to learn node representation. Based on the learned node representation, the agent, which is a policy network, will make a decision of which node or which edge to be removed, so as to disrupt the network. So after removing some nodes, we get this intermediate graph. It's used into as the input to some simulator to simulate the recovery of the network, so that we get the new graph at T+1. Now we can measure the functionality, such as the average short path length of GT and GT plus 1. So the difference would be the reward, right? For example, if we want to reduce the average, if we want to disrupt the network to maximize the average short path length, right? Then the reward would be the average short path length of this graph minus the average short path length of this graph. And we want to train our multilayer graph neural network and the agent so that it can make a decision, make action to maximize this reward. So that's the basic idea of our framework. We have implemented this multilayer graph neural network and agent part, but for the simulation part, we have some difficulty for doing that because we are not very clear about how the network would behave in order to recover. So we are still trying to figure this out. But based on the preliminary experimental results we have without the recovery part, it's quite promising. The experiment we did is try to remove X% of nodes to maximally increase the average short path length of the graph. We compare with some classical methods such as degree-based and betweenness the centrality-based method, where they first calculate the centrality of node, then remove those nodes with the large centrality. So the score here denotes the average short path length after removing 5% nodes and 10% nodes. So as you can see, our method outperform all the baselines. So the next step of this project is try to integrate this simulation part into the framework. So the last task is on transfer learning on criminal network. The goal is like this. The target criminal network, which is denoted as GT, is often noisy, lacks node information, and contain node label information, and contains unseen relations. So we want to transfer some knowledge from a more complete criminal network called a source graph to the target graph to alleviate these issues. The main challenge here is how can we align the node representation of the source graph and target graph into the same feature space so that some link predictor or classifier trained on the target on the source graph would be usable to the target graph. The approach we take is align node embedding of both the source graph and target graph using adversarial training, making them to follow the same distribution. Here's an illustration of the framework. We have the source graph and a target graph as input to some multilayer graph neural network to learn node representation. Right? Then we introduce a discriminator. This discriminator aims to differentiate if the input to it is from the source graph or the target graph. While we train this multilayer graph neural network to learn node representations that can fool this discriminator, making it unable to differentiate. Right? So if we have some node representation from the source graph and a target graph, makes the discriminator unable to differentiate if it's from source or from target, then it means that the source graph, the node representation we learned for source graph and the target graph, they already have similar distribution, right? So that we can use the classifier or link predictor trained on the source graph to the target graph to perform link prediction and node classification. So we also have some other components developed to make this procedure more effective. So I'm going to neglect that part. We did experiments on several data sets, including ACM DBLP, A-A and A-B. So the table shown here is the node classification results. Oh, by the way, the source attributed multilayer graph is labeled, and the target attributed multilayer graph is unlabeled. Okay, so we would like to train some classifier on this source graph and apply this classifier on the target graph by utilizing the framework shown here. So in the result, this means we ACM is a source graph and the DBLP is target graph. We wanted to transfer the information from ACM to DBLP. Similarly, here means that we want to transfer information from DBLP to ACM. The last row is the performance of our framework. It's significantly outperform all the baselines. So we also changed the loss function of node classification to link prediction and tested on some data sets. So the setting is like this. The source graph has the complete links and the target graph is sparse. So we want to train a graph neural network by using both the, sorry, there's a typo here, by using both the source and the target graph to do link prediction on the target graph. Okay. So the result in the last row shows that our framework achieves the best performance. So we also developed a toolbox for multi-layer network analysis. The toolbox is named as the multi-GL. It's mainly composed of 3 modules. The first module is for data preprocessing and visualization. It has the function to load the various kind of data formats and do some preprocessing and simple measurements, such as calculating the network centrality for this multi-layer graph and visualizing this attributed multi-layer network. And the algorithm module includes the representative and the state-of-the-art algorithm, such as the MGCN, GATNE, XGO, HAN, DMGI. And the downstream task and the evaluation module include some code for node classification, node clustering, link prediction, and evaluation metrics to evaluate the performance of each task. So a preliminary version of the toolbox is available at this GitHub link. So currently it's implemented in Python and don't have GUI available. So the students who develop this toolbox has graduated. So we are currently trying to recruit some other students to develop some GUI for this toolbox. Okay, so as for the project's application, we developed a state-of-the-art technique and toolbox for multi-layer neural network analysis. And many real-world graphs, they can be represented as the multi-layer attribute graph, such as the social networks, the criminal networks, the finance networks. So the algorithm designed in this project and the toolbox would be very helpful for criminal analysis on various different kind of complex graphs to perform link prediction, node classification, network disruption. And let me just summarize the project results. Currently, we have one paper on task 1.1 accepted by Sonum 2024, one paper on task 1.2 recommended for revised and resubmitted to ICWSM 2025. So we have revised and submitted in September. And we have one paper on task 3 in submission and another paper on task 3 to be submitted in October. We are currently working on task 2, try to integrate the simulation part into our model. And an initial version of the toolbox is available at the GitHub. As for transition of the talk, of the tech, we will discuss with the Office of Technology Transfer at Penn State about potential patent application and technology transfer after we finish task 2. So that's all about my talk. Any questions?
Great. Thank you very much, Suhang.
Thank you.
I'm happy to moderate questions. You folks out in the audience are welcome to put their questions in the chat, but I do see that John has just raised his hand. So John, please go ahead.
Yes. Good morning. I have a question about the data. So we have a project here where we're utilizing telephone data and we're matching that up with various layers of financial data to identify networks. So part of that project is to identify the knowns, but the bigger part of that project is to identify the unknowns, individuals that may be um, linked to networks we know about, but maybe in and of themselves part of bigger networks. And because of the multi-layering, because this project seems to use different sets of data, I'm wondering if this would be the type of challenge that this project could help clarify, or whether that would be, sort of in line with what you guys are trying to do here.
Oh, yes, that's a very good question. Actually, the data is the one big challenge for our study. So as you can see, the data we used here are first some publicly available multi-layer attributed graph. That's actually on citation network and some product network, product review network. So these two are not these four data sets are not criminal network. That's why we also constructed some synthetic criminal network data, so to facilitate the evaluation of our module. So the problem you mentioned, I think it's I'm not very clear about that problem, but things that it's a little bit different from the problem I'm starting here. So the problem I'm starting here is that we have a multi-layer graph look like this, right? Where different layer denotes a different relationship, and all the layers they share the same set of nodes, right? So for example, we know that all these three nodes they denote one criminal, and these three nodes they denote another criminal. So we know this relationship, but they just have different relationship in different layer, and we try to develop some algorithm to analyze such kind of criminal network. The one you mentioned seemed to be more like a network alignment problem. I'm not quite sure. Maybe so seems that you have some kind of graph, right? And you have another graph. You do not know the relationship between the two graphs. You want to maybe connect one node in one graph to another node in another graph. Is my understanding correct?
Yeah, I mean, part of the challenge is, getting to that. We know what we know, but we don't know what we don't know. And then what we're trying to do is trying to utilize data to at least get a clue about what we don't know, to at least begin the process of identifying an individual or an entity that, that's where the predictive part of this, sort of came to me, to see whether this is somebody who, could be bigger than what the data shows and needs additional, other types of investigative, or needs investigative action in order to complement what the data is showing.
Oh, okay, I see. Yeah, so that's kind of maybe linker prediction problem. So you have the data, and you know some relationship, and try to train a model to predict the missing relationships, some
Yes,
relationship you
correct.
unknow. Yeah, yes.
Yes,
Yeah.
correct.
Okay, I think the graph neural network would be quite helpful. So probably you would need something called a heterogeneous graph neural network, because I think you have a graph of different type of nodes and different type of relationship, right? So we'll need to have, so essentially it's a heterogeneous graph, and we'll need to develop apply some existing heterogeneous network, heterogeneous graph neural network to do linker prediction on this graph.
Okay, thank you.
Yeah, thank you.
Great. And John, we would be happy at CINA to set up a meeting offline with your team to talk to Dr. Wang in more detail. If that's interesting to you, just reach out.
Yeah, that would
sure.
be great.
I'm happy to do that.
Yeah, that would be great for us too. So I'll circle back.
Yeah, we offer that opportunity to all of our DHS partners on the line. This research is your research. The PIs are here to explain it to you in whatever level of detail you're interested in. Of course, Dr. Wang's toolbox, the first version is available on GitHub. We would be really interested in seeing folks in the components download it and try it out in their test environments. And we're happy to facilitate those kind of conversations. Great. More questions? Feel free to put them in the chat. It's pretty small group this morning, so so if you just raise your hand, that's fine too. Okay. In the meantime, I'll ask a question. Suhang, your research is on multi-layer criminal networks. Have you also considered dynamic criminal networks? And maybe you can also explain the difference between those.
Yeah. So dynamic network is a very interesting and challenging research direction. So essentially for dynamic network, we can have a new node join at a different time step. We can have a new node join the network and the new links created or some existing edge disappear during the time. So it's a very challenging problem because we'll need to model this dynamic of the graph to capture some dynamic patterns to make prediction forecasting. Currently, we haven't started working on that, but that's some projects that we are thinking about in the next step. So I'm sure that there's a lot of opportunities for developing novel graph neural networks to handle the dynamic graph. Yeah. So one simple way that many existing work have done is try to combine some time series model such as long short-term memory (LSTM) to handle the dynamics, to capture some periodicity or temporal pattern of the graph, and meanwhile use graph neural network to handle the graph structure. So we are thinking about like extending this project as the dynamic multilayer graph, to handle the dynamic multilayer neural network, where there's no existing work yet.
Great, thank you. And I should clarify. I know that some of the folks on the line are a little bit newer to CINA. These projects are under a cooperative agreement with DHS, which stipulates that we are unable to share data back and forth. So Suhang mentioned that that he used publicly available data. And there are also some constraints on the use of publicly available data, but what is not possible under this cooperative agreement is for components to actually share data with researchers and to let them use it. And there are good reasons for that firewall. It does make the transition a little bit more complicated. And that's where, we sort of at the end of a project like this, we're really eager for components to use the techniques on their own data within their own walled garden, and let us know how it works. And our researchers are available to help troubleshoot. They can't actually sit next to you and look at the screen because of the terms of our cooperative agreement, but they can help with more general analytic questions and applying the techniques that they've developed. Great. Another question, Suhang. How could you use this method with other networks? So social networks or financial networks?
Yeah, so actually like many real world network, they can be represented or treated as a multi-layer graph. For example, for social networks, in that case, each node would be one user in the graph, in the social network, right? And then in social network, we have different kind of relationships. For example, in Facebook, we can have one user follow another or be friend with another user, right? So one layer of the graph would be the friendship relationship. And meanwhile, we can have one user liked or commented another user's post. So the second layer could be the like or comment relationship. And so we can also convert other kind of behavior into the third layer, fourth layer, so that we can obtain this multi-layer graph. And meanwhile, we have the user profile and user posts. They can be converted into the node attributes, which forms this multi-layer attributed graph. So then we might be interested in predicting the preference of each user, detect malicious behavior of each user, or detect malicious account of each node. So that's one example of how we apply. So I mean, like once we construct the multi-layer attribute graph for this social network, then we can apply the technique we just mentioned to model this multi-layer network.
Great, thank you. Any more questions from the group? Okay, Suhang, to kind of wrap things up for us, why don't you tell us a little bit more about the toolbox?
Yeah, sure. I have the slide. The toolbox, so I have just introduced the overview of the toolbox, and it's written in Python. So currently, we don't have a graphical user interface available yet. So we are thinking about developing that to make the toolbox easier to use. And we have fully tested the toolbox, and the performance looks quite good, very similar to those papers, so to the original paper of the methods. I mean to the results reported by the original paper, and so this is actually one master thesis of a graduate student. So we have documents available as his scholarly paper, and we are currently trying to make that document more clear so that it will make the end users to more easier to understand how to use it. So currently, since there's no GUI available, if you want to use the toolbox, you need to download the code and then prepare the data, use our module to the code to load the data. Then you can apply the algorithms implemented in this code for node representation learning on multi-layer attribute graph, and then apply the module of downstream task and evaluation module to do some node classification, node clustering, link prediction. So yeah, I mean, like now you will need to write a little bit of code in order to use our toolbox. So later on, after we develop some GUI, it will be easier to use. Maybe just click some buttons.
Great. So in other words, to partner in the transition, a component would still have to have a certain level of technical expertise. But the upside is that this is all open source, and DHS already owns all of the output from this project. And so, you know, we're at CINA, we are not trying to sell you any sort of tool. And in fact, we want to make components integral parts of developing them. And so your team would really be kind of at the ground floor in defining user needs. And then, developing a GUI could be an excellent sort of next step, which could be undertaken under CINA's basic ordering agreement. Great. Any more questions? All right. If that's all, then I will. I'll bring the session to a close. Thank you all for joining us, and special thanks to Suhang and to your team for an excellent presentation and for all your good work over the course of this project.
Yeah, thanks very much for CINA and the DHS for supporting this project.
Okay. Thanks, everybody.